Copyright 2013, Math Diagnostics and Intervention, all rights reserved. We're going to take a look at multiplying expressions that have exponents. First off, in order to multiply expressions that have exponents, the base of the two expressions must be the same. In other words, I have to have something like x squared times x to the third. The x is called the base, and the 2 here is called the exponent. In this expression, x cubed, x is called the base, and 3 is called the exponent. Because these two expressions, x squared and x cubed, have the same base, we can combine them using what is known as the multiplication rule for exponents. Let me give you the rule for multiplication of exponents. First, if we have an expression of x to the m and we want to combine that with x to the n, that is always going to be equal to x to the m plus n. This is a rule that you're going to have to memorize, and you will be using it for the rest of your mathematics career. Let's take a look at an example. Let's go back to our x squared times x cubed example and take a look at why this might be true. If we take a look at our definition of exponents and we take a look at x squared by definition is x times x. Also by definition, x to the third, or x cubed, is x times x times x. Using our definition of exponents again, we have x as a factor 5 times, and that means that this simplifies to x to the fifth. I can rewrite x to the fifth as x to the 2 plus 3. And because x to the fifth was equal to our original expression here of x squared times x cubed, we end up again with x squared times x cubed. And although this is not a proof by any means, this is an example that kind of tells you why the rule for multiplying exponents might be true. Now let's take a look at an example of how we might use this if we encounter a problem such as y to the sixth times y to the eighth. Our rule for exponents, when we're multiplying numbers that have, or expressions that have the same base, is that we add those exponents. So that's y to the 6 plus 8, which is y to the 14th. And we're done. That's as far as we can take this problem. One thing that tends to mess up students sometimes is when we have a variable that does not have an exponent attached with it. If I have y times y to the fourth, one of the things that students don't understand sometimes is that this y without an exponent is really y to the first. And once we determine or acknowledge that y is y to the first, we can then just simply follow our rule for exponents and say, oh, that's just y to the 1 plus 4, or y to the fifth. Now, so far we've only dealt with positive integers, but there's nothing special about the rule for exponents. Our m and n, when we look at x to the m times x to the n, being equal to x to the m plus n, it doesn't say that m and n have to be positive counting numbers or integers. M and n can be anything. If we take a look at x to the negative sixth times x to the ninth, again, the rule doesn't change. I simply take x to the negative 6 and add the 9 exponent to it, and we end up with x to the third. There's also nothing that says that these have to be integers at all. We could have x to the 1/2 times x to the 1/3, and we're still going to add those exponents. We're going to take x to the 1/2 plus 1/3, find our common denominator of 6, and combine these as 3 over 6 and 2 over 6. So that gets us x to the 5 over 6 power. So the rule didn't change when we went to fractions. And in fact, that rule for the multiplication of expressions with a common base is going to be add those exponents no matter what those exponents are. So to review, when you have two expressions that have the same base, x to the m times x to the n, you're going to take the common base of x in this case and simply add those exponents. Again, this is a rule you're going to use frequently and you must memorize.